the microphone right now to my colleague Giacomo, and he will be introducing the virtual piloting part. Giacomo, the floor is yours.
Thank you. All right, so we'll go through the typical workflow of a virtual piloting exercise. What we typically start from is a real sample, real data that we feed into a virtual representation of the plant, simulating an ozonation plant that takes the effluent of a wastewater treatment plant or any other stream, and then we run simulations and we mimic what would happen if we apply an ozone dose in terms of micropollutants removal or bromate formation. We can test a large number of scenarios, and normally in the feasibility study, in the technology assessment stage, we run in a few weeks a huge number of scenarios. Now, when the data are available, then we feed the model with fixed steady state conditions or dynamic conditions, and the model, the mechanistic model is behind this what we call the virtual installation. What we see in front of you, it's really the virtual pilot plant in which the flow, the water matrix goes in through bubble columns, in which the ozone dose can be delivered. It can be designed in many ways in accordance with the client, and then the ozone dose can be delivered with many strategies like flow proportional, DOC proportional, and many others. So in this specific example was a water matrix from an effluent of a municipal treatment plant in Sweden, in which we tested, we calibrated the model on standardized ozonation test together with the experimental data, and then we ran the model in the virtual pilot installation in different doses of ozone, and injecting the ozone in multiple points of the installations, because distributing the dose has an effect on the micropollutants removal, but mostly on the bromate formation, and in different conditions, in maximum flow, minimum flow, also having specific composition of the water, because when a rain event hits a plant, then the water composition changes. What you can see here in a nutshell, without going into much detail, is that the highest scenario, the highest dosage of ozone gives, if it's dosed in one column, then it gives the highest local ozone concentration, which are then depleted along the installation, right? When we explore the same dose at the maximum flow, but across 3 injection points, the local ozone concentration is distributed across the whole installation, across multiple points, and then you locally reduce the amount of ozone in the liquid. And what is also one interesting point of view in terms of assessing the size of the generator, doing an initial assessment is also to establish the size of the generator that we would need for such a control strategy. Then beside this, we also look in terms of bromate, what happens, and micropollutants removal. But in this case, you see the bromate results for each of these scenarios, and how a very high ozone dosage would bring a too high bromate formation. And then there are more, let's say, smarter ways of distributing the same dose or achieving the same micropollutants removal with a lower dose. and allowing us to minimize the bromate at very, very low values. Now, I will take a moment and I will hand the mic to Roberta for the live demo. Thank you.
Yes, thanks, Giacomo. All right, so now what we are looking is a real-time dynamic simulation in our virtual environment. So what you can see here is a virtual pilot of a secondary effluent ozonation plant. Ozone dose is injected in these first two bubble columns, first two units, and then we let the ozone interact and be in contact with the water in the remaining units. So here we are currently running a dynamic simulation. Here you see the influent flow rate in blue. You can see that there is a combination of dry weather condition and rain weather condition, especially in between day 3 and 4. We have a heavy rain event. And together with that, we can also look at the dynamics of the water metric composition. For example, in green, we can see the dynamics of the DOC concentration with a peak just before when the rain event starts, followed by a lower concentration, so a dilution during and after the rain event. Similarly, the ammonia concentration with an increase just at the beginning of the rain event and big dilution with value close to 0 during and after the rain event, and then average concentration. Now we're running a simulation with a PID controller, which means it's a DOC proportional controller with a set point of 0.5. So the ozone to DOC ratio is 0.5. And then we can look at some effluent concentration, effluent variables in terms of ozone residual, making sure that all the ozone is being depleted and is consumed before it gets discharged. And we can also look at bromate formation, for example. Here in the bromate formation, we see some particular and interesting dynamics. So we have like a baseline concentration, which is very low, around 0.2 micrograms per liter, with some peaks. And especially in the rain event, we see an increase of bromate. First of all, we can ask ourselves the question why we have this increase in bromate during the dry weather condition. And we can find an answer if we look deeper into the ammonia dynamics. You can see that in certain moments of the day, the ammonia concentration goes very low. And we know that ammonia has an important role in the bromate formation chain, because if ammonia is present, it can sequester the isobromous acid to form bromamines and preventing the bromate to be formed. So when ammonia is lacking, then bromate peaks can appear. And this is even more pronounced during the rain weather condition, not only due to ammonia, but also due to the certain particular behavior that happens during the rain weather condition in terms of radicals. So here we're looking at micropollutants removal, average removal along the dynamic removal, actually along the days, along the time, and we can have very fast removing compound and low reactive compound that are hardly removed. What is interesting to see here is that during the rain event, we have an increase of micropollutants removal. Why? Because with the dilution of the water, the scavenging of the radicals is less pronounced, which means that we have more production of hydroxyl radicals, leading to higher micropollutants removal and, as we can see, higher bromate formation as well. So with this fast and dynamic simulation, we can already think of possible improvement in the operations, so possible smart dosing strategy between rain and dry weather condition. And with that, I'll hand it over to the presentation again.
Perfect. So Roberta, thanks for the demo. So if you have any questions, yeah, they are coming in. Great. Yeah, I was just going to say, drop them in the Q&A, but it's already happening, which is very good. We will come to the Q&A very soon. So to end this section on virtual piloting, business case is very important. So if you look at on-site piloting versus virtual piloting, there are very big fundamental differences. Typically, the cost, what we see is in on-site piloting, if you want to do it longer term, it typically takes 100 to several hundreds of thousands of euros if you include man hours, renting or buying a pilot installation, analytical costs. So this is really the business case of a real customer, three full-scale plants in the Netherlands. And virtual piloting can lead to up to 90% cost saving. And typically where you are in the range of 80–90%, which is very, very significant there. Now, cost is not everything. Time also, because piloting really takes 1 or multiple years. It can take multiple months. It really depends on the scope, how broad you set it up. But typically it's significant. Only already starting it up, getting acquainted, troubleshooting, it already takes quite a while. While actually a full virtual piloting cycle is 1 to 2 months. You typically also have some issues on site, like experience issues or safety issues, which are not present in virtual piloting. And the questions that are typically unanswered after on-site piloting, we try to really answer with virtual piloting, because you can test all of these scenarios. So for example, this simulation Roberta has shown, you can really start doing a lot of what if scenarios. And this is what we are going to come back to in a demo of Giacomo on a drinking water digital twin. Okay, so we will be showing that. So good. So yeah, it's quite a big difference. And there are also hybrid modes. In some cases, our clients do a real piloting in combination with the virtual piloting. And then you can keep the one shorter, maybe complement the other and expand the information. So a lot of possibilities here. So let's go to the Q&A and see if there are any questions that came in. Okay. So maybe Giacomo, a question for you. Yeah, if you can come to the stage. So we have a question on the variables. Each micropollutant, is it really literally calculated independently in the model?
Correct. We call them state variables when they're independently calculated. And then each micropollutant, and now they're more than 70, around 100, something like this, are treated as a separate variable.
Yeah. And then coming also to the micropollutant still, which input do we use, for example? Do we let them change during a rain event? Or do these concentrations come in at a constant rate, typically in the model?
Yeah, so that's a good question, and it relates to others that indeed refer to the type of input. The type of input can be dynamic or can be steady. It depends what is available and what is the objective of the study. The dynamic simulations can also include variable micropollutants concentration, and in particular, it's interesting to be included there, taking in consideration the effect of the biological plant. So the biomass and the biomass concentration variability will have an impact on the removal of some micropollutants, and thus on their concentration downstream that arrives at the ozonation plant.
Yeah. Okay. Thanks. So yeah, with regard to the dynamics, if you're working at the drinking water sites, you are way less faced with these dynamics. So let's say you can really see, let's say affluent ozonation as an extreme example of a dynamic ozonation system, if you look at it from that point of view. So dynamics also in micropollutants or fluctuations in DOC or rain, for example, is way less present in drinking water, where it's more consumption or production based. Good. Yeah, what input data? That's a final question of this section. What input data is used for bromate modeling, bromate prediction?
Yeah, so the bromate formation it's a very complex story. There are many variables involved. There are many compounds, but in general, the bromide, the Br minus concentration is the most influential, the most important to know, as influent concentration into the plant that arrives. Then alkalinity, pH, all these other compounds have an effect. Ammonia, as we have seen from Roberta, has a role in the final bromate formation. So the more we know, the better, but we can also make assumptions based on the geographical location and type of water. Yeah.
Okay. All right. Good. So more questions, definitely welcome. Just put them in the Q&A. We will come back to another Q&A section later. Perfect. So yeah, that's to summarize that a bit. That's the difference between a data-driven model and a mechanistic model. We try to put in a lot of chemistry in the AMOZONE model, which means that if we go to a new plant with a very limited effort or very limited new data, we can have the model up and running.